Okay, in the last lesson we learned the fundamental theorem of calculus. So now we have all sorts of jokes at our disposal. For example, what's the value of this integral? I always like to throw that one at my students. The antiderivative of 3x squared is x cubed. And so you evaluate that from 0 to ice, and you get ice cubed. Okay, a little levity. Or another one, from 1 to cabin of 1 over x dx. Antiderivative of 1 over x is the ln of x from 1 to cabin, and you end up with log cabin. Okay, the ln of 1 is 0. So anyway, a little bit of fun there. Now, this reminds me of something which I just didn't quite finish doing in the last lesson, which I want to do just for completeness, rather than just have you believe me. And that is that the derivative of the ln of the absolute value of x is equal to 1 over x. What's the advantage of saying this rather than the ln of x? The ln of x has a domain just for positive values. The ln of the absolute value of x has this as the domain. So it's a function with a larger domain. You can do more with it. So it's a little nicer to be able to say that the antiderivative of 1 over x is the ln of the absolute value of x. You can do a little bit more with it there, a little more general. So anyway, let's prove it. So let's prove this fact. So how do we prove it? Well, if x is positive, then the derivative of the ln of the absolute value of x is just going to be the derivative of the ln of x. If x is positive, this is equal to this. And we know the derivative of the ln of x is just equal to 1 over x. No problem. If x is negative, then the derivative of the ln of the absolute value of x is equal to the derivative of, well, let's see, if x is negative, then the absolute value of x is the opposite of x. And the opposite of x. So it's going to be the ln of the opposite of x. And what is the derivative of this? The derivative of the ln of anything is 1 over that thing times the derivative of the inside, which is a negative 1. So by the time you do that, you see you end up with 1 over x again. So whether x is positive or negative, the derivative of this function is equal to 1 over x. So that's why this is true and why this is also true. Okay, so that was a little bit of mopping up to do, and here's just one other thing to do, just by way of reinforcing what we've already learned. I mentioned in the last lesson that if we don't have the limits of integration on, then all we're doing is just asking for the antiderivative. So for example, if I were to go x to the 5th plus cosine of x plus e to the 3x plus 1 over x plus 5, for example, dx, then I'm just asking for the antiderivative. And you can, in the same way that you take the derivative of each one at a time, you can just take the antiderivative of each one at a time for the complementary reason. So the antiderivative of this is going to be 1/6 x to the 6th. The antiderivative of cosine is sine of x. The antiderivative of e to the 3x is e to the 3x times 1/3, right? We have the antiderivative of 1 over x, we just said, is the ln of the absolute value of x. The antiderivative of 5 is going to be 5x. And then you always throw on your c just to indicate that you can throw any constant on there at all, and you still have an antiderivative of that. Okay, so that's the idea. Let's try one more just for practice. 1 over x cubed plus square root of x plus x squared plus 1 over x plus x times x squared plus 3. Okay, I'm throwing a whole lot at you at once here. Okay, well, the reason I did this is just to indicate that you can do algebra as needed to simplify things. I'm going to rewrite this as x to the minus 3. I'm going to write this as x to the 1/2 power. I'm going to do a little algebra on this. X squared over x is the same as x. And then 1 over x is 1 over x here. Here I'm going to do a little algebra and just multiply this through and get x cubed and then plus 3x. So that's all stuff you can do. And then take the antiderivative. It's going to be what? You add 1 and divide by it. So it's x to the minus 2 divided by minus 2. Plus, add 1, you're going to get x to the 3/2 divided by 3/2 is the same as multiplying by 2/3. This is x to the 1 power, so it's going to be x squared divided by 2. 1 over x, of course, that's the ln of the absolute value of x. X cubed is going to give us what? X to the 4th divided by 4. And finally, 3x is going to be x squared. You divide by 2, it's going to be 3/2 x squared plus c, something like that. So those are antiderivatives. In Calc 2, we're going to actually start it in the next lesson in Calc 1 here. We're going to learn other ways to find antiderivatives of functions in the same way that we found ways to find derivatives. Derivatives was very mechanical. We had the product rule and the chain rule and the quotient rule. Finding antiderivatives is a little more of a hunt and search technique where you have to kind of try different things. It makes it a little more fun. But we'll learn some of that coming up in the next lesson, and then Calc 2 is where you spend a lot more time finding other ways of finding antiderivatives. The one thing I want to do right now is just to explore one more time why it is that this strange relationship happens where the derivative of the integral gives you the value of the function. Why should that be? Why should it be the case that if you want to find the area underneath a function that you take the antiderivative? Well, why does that even make sense? I remember after having had calculus quite a while later, it just hit me. I thought, well, my teacher probably explained it to me, but all of a sudden I was just kind of curious. Why is this the case? So here's my best way of explaining it to folks is to do this. Let's let f of x stand for, again, the area underneath this curve, and I'll be a little more specific this time and say it's the value of the integral. So from here to here, it's going to be the area, which is always a positive number. From here to here, what's happening? This is going to be a negative contribution, right? Because the value of the function is negative. So the integral from here to here would be a negative value, and then the integral from here to here would be positive again. Okay? So let's just think about it like this. If you were to ask, if you were to be walking along this road, and say this is a road, and say this is farmland here, or pasture land, and here you have a river or a fence like this that gives the boundary, okay? And the boundary crosses the road and it goes up like this again. And suppose you were told that as you walk along this road, that all the land that you pass becomes yours. All the land on your left-hand side, as you pass it, all this land becomes yours, okay? You just walk along at a steady pace, and every step you take, all the land you pass becomes yours. And then, any land that's on the right-hand side of the road, down here, any land you pass is land you have to give up, okay? So let's just think about it. As you're walking along here, you are gaining land, agreed? You are gaining land. When are you going to be gaining land the quickest? Okay, from here to here, you just gain that much land. As you took the next step, from there to there, you just gain that much land. At what point will you be gaining land at the greatest rate? Well, do you agree? It's going to happen right there. Right there is where you're gaining land at the greatest rate. In other words, just look at it. The rate at which this thing is growing, this thing right here is the area underneath the function here, okay, the value of the integral. The rate at which this thing is growing just depends on the height of the function. Well, sure, that makes total sense. The rate at which the area is growing depends on the height. If the height is greater, as you step from here to here, the amount of land that you've just gained is the greatest. From here to here, you're still gaining land, right? Okay, the F is decreasing, but this thing is still increasing because you're still gaining land as you go from here to here. From here to here, you're still gaining land. From here to here, you're still gaining land. Now you're giving it up, okay? So if we wanted to, we could even say, let's graph capital F of x. Okay, let's graph it. Okay, well, let's call this point 0 right here. And the first thing we need is what's f of 0 going to be? F of 0, let's change this to the point 0 here. So that's we're starting right here at the origin. So f of 0 is the amount of land that you've covered if you haven't walked at all. If you haven't walked at all, how much land have you passed? You haven't passed any at all. Agreed? So it's going to look like that. Now, what else do we know about a function? Where is it increasing or decreasing? We know that f, any function, is increasing when the derivative is positive. Agreed? When the derivative is positive. But notice that the derivative of this function, right here, this is your okay, the derivative is just equal to small f of x. Agreed? So capital F is increasing wherever small f of x is greater than 0. Well, that jives with what we just said, right? As you're walking down this road, all the land that you pass, as long as small f is positive here, you're gaining land all the way. Agreed? So it's going to be wherever small f is greater than 0. So let's label some points here. Let's call this, I don't care, let's call this 5, call this 10, call this 11, call this 12, call that 13. Okay? So in other words, where is this thing increasing? This is increasing when on the interval from 0 to 10, and then from 12 to 13. Union from 12 to 13. Okay? Where is f decreasing? F is decreasing whenever its derivative is less than 0, and the derivative of capital F is just equal to small f. So it's wherever small f is less than 0. So that's going to be on the interval from 10 to 12. Okay? How about this one? Where is f concave up? F is concave up whenever its second derivative is positive. The second derivative of capital F is just the derivative of small f, right? Look at here. This is equal to this, so the second derivative of capital F implies the first derivative of small f is greater than 0. Where is the first derivative of small f greater than 0? Well, where's the slope of small f greater than 0? It's going to be from 0 to 5. And from where to where? From 11 to 13? There you go. And finally, where is f concave down? That's going to be where the second derivative is negative. The second derivative of capital F being negative means the first derivative of small f is negative. Where's the derivative of this function negative? Obviously from where? From 5 to 11. Okay? So now, unfortunately, I didn't leave myself any room. Let's see. Let me get rid of all this stuff and just put in increasing, decreasing, concave up, concave down. Okay? And we recall that f of 0 is equal to 0. So what's it going to look like? Okay? It starts at 0. Here's 5. Here's 10, 11, 12, 13. I kind of scrunched those all together. Anyway, from 0 to 10, it's increasing. It's concave up from 0 to 5. So from 0 to 5, it's concave up and increasing. That's what it means to be concave up and increasing. Once you pass 5, it's still increasing until we get to 10, but now it becomes concave down. So until you get to 10, it's still increasing but concave down. What happens once you get to 10? Now it starts decreasing. It decreases to 12. It's concave down until you get to 11. So there you are at 11. Then, once you pass 11, it becomes concave up. It's going to be concave up for the rest of the time now. It's still decreasing until you get to 12. So there you are at 12. It's concave up and decreasing. And then once you pass 12, it is now concave up and increasing. So it's going to look like that at 13. Okay? So here's your capital F right there. This is the function right here, which basically tells you how much area is underneath this function, right? From here to here, you keep increasing. Once you get to 10, then you stop increasing, and now you're starting to give it away. That's why it's decreasing here. And once you get to 12, you start increasing again. And here, the rate at which you're increasing continues to increase, right? As you walk from here to here, you every step you take, you're getting more land than before. So that's concave up. From here to here, you're still getting more land, but the rate at which you're getting land is going down. See, that's why it's concave down there. Okay? So this is good for you to do. Let's do one more just for the practice. But you should realize that this function here tells you what the area of this one is, and this function here tells you what the slope of this one is, right? The slope of this one is small f, and there's small f right there. So if you want to know the slope of this at any point, the height of this graph gives you the slope of this one. So one other thing to notice is that this thing here was not differentiable there, but this is nice and smooth. Typically, whenever you take the antiderivative of a function, you get a smoother, nicer function. That's just a general rule in mathematics. When you take derivatives, things become nastier. When you take antiderivatives, you kind of smooth things out. And there's just one example of how that kind of smooths out. So let's just try one more. Same idea, but just this is a real important example. Okay. I don't know. Looks pretty similar, doesn't it? Should we do one more? Come on down like that. Okay, let's let this be 1, this be 4, this be 7, 8, 9, 10, and 12. Okay, so there's the function. Okay, first thing to notice is that f of 1 is going to be 0 again, right? Because, not small f of 1, capital F of 1. Capital F of 1 is going to be 0 because capital F is the value of the integral from 1 to x of small f. Okay, so capital F of 1 is going to be 0. And where do we go from there? If we want to know where is f increasing, it's where f prime is positive, which is where small f, well, let's just write it like this. Capital F prime is equal to small f of x is positive. And where is that positive? It's positive from 1 to 7 and from 9 to 12. Agreed? Small f is decreasing whenever the derivative, capital F is decreasing wherever its derivative, which is equal to this, is negative. And where is that negative? It's negative from 7 to 9. I never worry about whether you include the endpoints or not. Not a big deal. F concave up, I'll just write up. That's where its second derivative is positive, but its second derivative is going to be equal to the first derivative of small f. Where is the first derivative of small f positive? From 1 to 4 and from 8 to 10. Together with 8 to 10. And finally, where is f concave down? It's where the second derivative, which is equal to the first derivative of small f, is less than 0. This is where it's greater than 0. And that's going to be where? Where is the first derivative of small f? Negative. It's negative here and here. So from 4 to 8, together with 10 to 12. Okay, so see if I can do it same as I did it before. Didn't give myself quite enough time, quite enough space here. I have to kind of shift it over. So here's 1, 4, 7, 8, 9, 10, and 12. So starting at 1, what's happening? It's increasing and it's concave up until you get to 4. So from 1 to 4, it's increasing and it's increasing and concave up. Once you pass 4, it's still increasing until you get to 7, but now it's concave down until I get to 8. So it's going to be concave down, so it's going to be increasing until I get to 7. It's still concave down, but now decreasing until I get to 8. Once I pass 8, it is now concave up, and it is still decreasing until I get to 9. Okay? Once I pass 9, it starts increasing again all the way to 12. So it's going to be increasing and it's going to be concave up until I get to 10. So until I get to 10, it's increasing concave up. Once I get to 10, it's still increasing, but now it's going to be concave down again. So it'll look something like that. So you can almost do it easier just by thinking of this function and thinking about what's happening here. So this is capital F right there. This is the value of the function. Okay, very good. We've got one lesson left. As I said, we're going to learn one more method of finding antiderivatives, and then that's kind of where Calc 1 stops, and then Calc 2 picks up with a lot more methods for finding antiderivatives. So there you go.